Alrighty. Howdy, folks. Who's here with me? Let me know. Let me know in chat. We are back. It's going to be a great day. We have so much cool stuff to share and to learn. Let me get my screen shared here. All right. It looks like folks might still be making it through the ad block here. Let me just take a look at what's going on in Twitch. Open up my window. All right, so we've got some folks inside of here. Once again, if you joined us from the last session, do let me know in chat. Otherwise, if you're new here, obviously, if you didn't check out MongoDB 101, definitely let me know that as well. I'm looking forward to kind of kicking things off with y'all once again. Really excited, because we've got even more content that we're going to be jumping into. So today we're going to be learning about MongoDB Vector Search. All right, if you're unfamiliar with vector search and what it really is, it's pretty interesting stuff, especially when it comes to data, and especially when it comes to data week in general. So before we get into any of the good stuff, let's go over our agenda for today. Basically, we're going to be talking about a search technique called vector search that allows us to search using the same language that you'd use to describe your thoughts, your emotions, and feelings, also known as something called natural language. And we've got somebody in chat from the last chat. Thank you, Rosendo. Appreciate you. So yeah, natural language. And if you're starting to build like generative AI applications, it's really important for y'all to get familiar with this technique called vector search, because you're going to be using it pretty extensively as you're, building those things out. So here we're just going to cover the basics, but MongoDB has a more in-depth learning experience that you can try out after this workshop. If you really want to dive deeper, I'm going to be showing you the links as well, and they're going to be the correct links this time, which is really exciting. All right. So as I mentioned, the agenda, we're going to spend around 40 minutes walking you through a bunch of concepts. So first, we're going to talk about what vector search is. Then we're going to talk about how it works in MongoDB, and then also spend some time talking about tuning and optimizing your vector search queries. And of course, we'll have a Q&A. Going to be pretty interesting stuff here. If you've seen this one before, not to worry. There are a little bit of twists and turns that we're going to be taking along the way. So definitely nothing to worry about on that end. But outside of that, let me just check in on the Twitch chat as well. All right. Looks like it's still pretty quiet on the home front here. So let's just go ahead and dive right in. All right. So as I mentioned before, there is a lab that coincides with this workshop here, and you could actually access it here. If you want to follow along, you can do so, but really it's not necessary. It's just something that you can probably do to give you additional context as you're actually working through the content, as we're actually working through the content on this side. So no big deal. First things first, we're going to jump right into it. What is vector search? So vector search, for the longest time, so vector search is a little different from some of the traditional search engines that you may have seen previously. So basically, for the longest time, a lot of the search experiences on websites, they've been powered by a technique called lexical search. So this technique, it really just focuses on keywords. So you take a user's query and it'll fetch the results that contain the keywords that are inside of that query, and basically in a search field configured behind the scenes. So say you run an online bookstore and you're going to use lexical search to power the search engine on your website. If your user searches for Greek philosophy, they might see results like these. And obviously, all of these results here have the literal words Greek philosophy inside of them, hence why they were retrieved. Now, lexical search is really great when you know exactly what you're looking for. In that case, Greek philosophy. But let's say you were looking for something that was just related to Greek philosophy, or let's say you can't remember the exact title of the book, or even the topic that you're searching for, or the correct spelling of an author. Lexical search is going to fail you here because it's not able to actually make those connections that you would if you were, using something like vector search. So for instance, maybe you can only remember the color of the book cover, or I don't know what the book cover, like the images on the book cover. Yeah, these are things that lexical search isn't really going to be able to help you with. So there is another. So that's where vector search essentially comes in. It retrieves the search results based on the intent or the meaning of the query rather than the keywords. So it's basically lexical search, but with a lot of different layers added on top of it. So say you now updated your website's search experience to use vector search instead. The same query as before, Greek philosophy, is possibly going to surface results that don't contain the words Greek philosophy inside of them, but are very much aligned with the theme of Greek philosophy. So as you can see here, we've got Aristotle, we've got Plato, the Republic, and then we've got Plato, the Symposium. None of these have the actual words Greek philosophy listed inside of them. You could also search using phrases that describe a book. So, for example, a fantasy novel about a boy in a school of magic. And you'll see here, obviously, Harry Potter was returned along with other fantastical looking books that you might be interested in if you were interested in Harry Potter in the first place. Next, you're going to say, say you read the first Harry Potter book and you want to read the next ones in the series, or say you want to check out more books that are similar in theme. You could even search based on the cover image of the book. So here, we went ahead and put a PNG of the Harry Potter cover. And what we found was things that are very similar. So obviously other Harry Potter books. And then here, another one on the far right, a Wizard of Earthsea, which is very much similar to the document that we would have uploaded as an image for reference. So basically, to recap the difference between lexical and vector search, lexical search is going to focus on retrieving results based on exact word matches, whereas vector search retrieves based on the semantic similarity or the meaning or intent within the actual search parameters. So you'd use lexical search when you're really confident that your users already know what they're looking for, they're using common terms, or they're just very familiar with the content that's already being searched for. Whereas for vector search, you could use that to, if you're expecting a lot of ambiguous search queries or inputs, things that people don't exactly know what they're looking for, but can like describe it in a certain way and basically you'd be taking advantage of vector search in that sense, because you would be able to drill down to the meaning or the intent of the queries and then find relevant matches there. So basically lexical search is usually going to be like your V1 search option or the first pass that you make when you're building out an application. And then when you want to go in and just like update your application and give it a, make the search features there a little bit beefier, a little bit more robust, you're going to, and basically use modalities that extend past like text, but also include things like images and videos and audio, then you're going to go with vector search. It's just, basically a search function or a type of search that just allows you to have a lot more in-depth results from the queries that you're inputting. All right. Question here from Relaxing Mars. That's a very interesting name. I love it. Is there a summary/recording for the MongoDB 101 course? I want to review some of the topics covered in the presentation, and I wanted to see if there was any way to review the information presented. Absolutely. So we have a YouTube channel where everything is going to be recorded, and you'll have the videos there. So you can go ahead. Oh, and it looks like, awesome. Thank you, Tammy. It looks like someone has already beaten me to the answer here. You could go ahead and head over to that YouTube channel, to that YouTube link there in chat, and you should be able to watch the recording and go through it at your own pace. Awesome. So we've said the word vector so many times up until this point. So what does it really mean? So walking around a Home Depot store, you'll see items that are organized and located based on aisle number and bin number. So if you're unfamiliar with Home Depot, it's a big box store with a bunch of like supplies for people that like do construction or DIY projects. And it's a huge store usually. I don't know what kind of huge stores you have like around your area, your neighborhood, your country, whatever. All I'm saying is like when you think of a Home Depot, it's basically like a tiny like neighborhood onto its own. One of the biggest stores that you'll probably encounter. So they have a ton of aisles and numbers, and it would be impossible to find any information in there if they didn't have some sort of like organizational way of breaking down where the products are actually stored. So vectors are kind of similar in this sense because you can represent the location of the items inside of your database as an array of aisle and bin. And like basically that's what a vector is. So for now, just think of vectors as an array of numbers used to represent a particular piece of information. And so for an item in Home Depot, it's going to be a two-dimensional vector. Like You wouldn't need anything else. But in software applications, especially when you're dealing with a large amount of text and maybe like different other data types like images, audio, or video, 2D vectors or two-dimensional vectors aren't really going to suffice and won't really allow you to capture all of the distinguishing features of this type of information, which is why we use 3D vectors. So basically, we've gotten a good idea of what vector search is and what vectors are. Let's see what makes searching based on meaning or modalities other than text possible. And basically, that's where embeddings come from. If you were in our previous session, we talked about embedding and referencing. Embeddings in the vector search context are going to be a little bit different and the same at the same time. So basically, embeddings are going to be a numeric, multi-dimensional representation of a piece of information. This information can be anything. It can be text, it can be images, it can be audio or video. But what's special about this array of numbers or vectors is that they capture semantic qualities of the data, essentially characteristics of data that capture the meaning or the essence of it. So this way, if you were to plot your data in this higher dimensional space, semantically similar data or data with similar meaning ends up really close to each other. So as you can see here in the example, you have dog and cat that are somewhat close to each other, but not as close to each other as apples and oranges. Apples and oranges are both fruits, obviously. They're both round. They both they're both at the grocery store. Dogs and cats obviously are animals, but there are very there are a lot of different varieties of both dogs and cats that are both similar and dissimilar from one another. Here, at least apples and oranges, there are a lot more similarities between the two versus dogs and cats. So as you can see here, that similarity is represented by the space in which by the space that is between each of those entries or each of those vectors here. And the vectors are once again represented as an array of numbers. And basically, these are arrays of numbers that you can go in and embed into your database at a later point in time, which is why they're called embeddings, which is why it's a little confusing. But just remember, vector search embeddings a little bit different from embeddings and referencing inside of a document. So the next question is, how do you go from a piece of text or an image or audio to an array of numbers? So this is done by specialized machine learning models that they've basically been trained to convert all of this information into these numerical encodings. So there are specialized models for different modalities. And by modalities, I'm just referring to different types of data. So here it's like different modalities are going to be text, audio, image, video, or other things like multimodal models. So basically models that have all different types of data inside of it. And they can take that and translate the different modalities into the same semantic space. It's the way I would kind of like look at it is the model is taking in all of this information and sort of organizing it in a way that is logical, and then and basing it on like the differences and the similarities of each of the data entries, and then it's assigning a numerical value to each one. So that's kind of like the way I would look at it. In the lab that I linked earlier, there's going to be a walkthrough and an experiment of the multimodal embedding model that you can use, and it takes both images and text, and you can input them and map them to the same vector space. If you're curious about that, definitely check it out. It's inside of the chat as well. So definitely make sure you check that out if you're a little curious. There are also a bunch of different embedding models out there. So you're not the one that's necessary. Well, you can go in and create your own embedding model, but you're not necessarily going to be creating the embedding models yourself. It's going to be, you're going to utilize embedding models that already exist. And basically what's going to happen is you're going to take those numerical values that have been assigned, by like some sort of machine learning model to these like different pieces of data. You're going to take those values and you're going to include them into your database by embedding that numerical value into the documents that you already have. If you want to take a look at some of the cool embedding models that are actually available, you can do so here. Just head over to this link. Looks like I have a question here. Can vector search be used in LLMs or like a recommendation system? I mean, yeah, I would assume so. I mean, the LLMs are probably being embedded somehow, and then you can like if you have basically if you're using like a generative AI chat application, something like that, you would just be leveraging the LLM for the actual responses. The person that has built out the LLM and has like maybe created a database for all of the information that lives within it has already probably embedded this and is like basically you're leveraging that LLM using some sort of vector search function in order to get your generative response. Okay, cool. So to perform vector search on data, you need to generate embeddings for the thing you want to search on. This is basically what I was talking about before. And sorry, let me hide this real quick. And so here we're going to be searching for books. And so in our books document that look like this, you're going to see on the left side, we have several options. We can either search based on title, the synopsis, or with vector search. So even the cover image of the book, we can find an embedding model that embeds images, and that's going to help us basically convert our search function from like a lexical search over to a multimodal vector search. So adding embeddings to data in MongoDB is pretty easy. I was kind of talking about it before. All you need to do is add an additional embedding field to your existing documents, and it's as simple as that. So that's why I said it was kind of similar and the same. Embeddings come from the embedding models that you use, but then you also go in and embed the embeddings into a document. So that's why they are similar and the same. But at the end of the day, you get the idea. The embedding model is something that comes from like a third-party service, and then you're taking that and you are incorporating it into the documents inside of your collections so that you can actually utilize vector search, because then like all of the things inside of your database pardon me, inside of your collection, all of the documents inside of your collection are going to have some sort of semantic value associated to them. So if you're using the lab from earlier, you'll be able to kind of see this hands-on. So definitely check that out if you're interested in getting a little bit more hands-on with vector search. We're not going to be doing embedding on this like during this walkthrough in and of itself, but we will be taking a look at a really quick demo that I think is pretty cool. So let's go ahead and jump into this vector restaurant planner. And what I'm going to do is I'm going to go ahead and add the link into the chat here. So this is an application that the folks at MongoDB actually spun up as well. It's pretty cool. So we'll be able to kind of dig into the code here, and we'll be able to first obviously take a look at the functionality first. And it looks like I have a question. How do normal databases differ from vector databases? So a lot of just like standard databases are going to operate on a two-dimensional plane. Vector databases are going to contain data that have like some sort of vector embedding in them, like like one of the embedding models that we had referred to earlier, and they are going to also operate on a 3D plane. So basically, especially if you're utilizing different types of data, like different modes of data, so multimodal data. So like I mentioned before, it's going to be video, audio, imagery, text. If you're utilizing all of that data within the same database, you're basically going to create when you do like the vector search or you query that data, it's going to find items that are near the search parameter. So basically the way it works is your query also gets an embedding. So let's say like you have a database and you want to go back to, actually let's go back to the slides real quick in order for me to answer this question. All right, so here we have let's go back. What is vector search here? I'm trying to find those Harry Potter slides. Okay, so here, so in this example, what we did was we used an image of a Harry Potter cover, book cover, in order to search for other things that were similar. So basically as part of this process, what happens is your image that you're actually using as a query also gets an embedding inside of it. It gets one of those like semantic embeddings that we were referring to. And now that query is going to, like, now that embedding is going to be, like, you're basically going to like take a look at where those like similar embeddings sort of occur inside of your vector DB. And then for the results, it's going to basically it's going to, for the results, it's going to capture all of the things that are like very similar and distant, like basically like near the search query. So it basically bases it on distance inside of a 3D plane. And yeah, once again, like your query itself gets an embedding number, and then based on that embedding number, the vector search will spin up any results that are sort of similar or near that original query. So in this case, is bringing up things that would have been classified as close, like semantically close to the cover of to the first cover of the first Harry Potter book. And here it's bringing in like the second and the third one. I'm actually not sure. And then something that was also classified as semantically close. So hopefully that makes sense. That's like the main difference between a standard database and a vector database. Is that it's just the way that it stores the data essentially. All right. Back to our example. Let me just make sure. And sorry if that's sorry if any of that was confusing. All right, so here we're taking a look at a live example. And all right, so this is so this is going to be the MongoDB Vector Search restaurant. So here I'm going to look for something like restaurants with options for a large group of people with various dietary restrictions. We want it in Times Square, Manhattan. We want it to be, like not too, like, I don't want to like have like too large of a distance, but here I'm actually like tweaking it. And then I'm going to go ahead and get the restaurants. And while that's running, basically what's happening is I am creating another vector search here. Basically, I'm creating this prompt, which is going to be basically put through some sort of like generative AI filter. And then that's going to create a prompt for me on the back end to my database. It's going to map it some, and then that prompt is going to get some sort of semantic value from the embeddings. And then it is going to, and here obviously we're using some sort of RAG generation. And then, yeah. And then it's going to basically generate on the map, show us on the map where all of those restaurants or locations actually live. While that's happening, I'll go ahead and jump into the files and show you how some of that stuff works on the back end. And you'll see like, some of the embeddings in here as well. It's pretty interesting. So if we go into app.py, this one's using OpenAI here. So the interesting part is here. So we're searching the data. So basically the response equals, so basically this is generating the response, and it's using this this language model in order to generate the response for you. This is how it's actually getting the restaurants and checking inside of your collection which restaurants actually fit the like the search. And then here, this is the interesting part. When you're actually writing into the vector query, you're going to see it's obviously taking like, it has like these two things, these two prompts for the actual like OpenAI API. It's saying like, this is what you are, generate a response based on this, and then do this and this. And then afterwards, what it does is it actually goes in, it uses an aggregate pipeline to get the restaurants that are within the geolocation that you specify, and then the distance that you specify, and then it gives you a trip ID, and then generates the trip ID for you. Yeah, I mean, basically, if you want to dig into this stuff, check out the link that I sent you. But here is like, the vector query search. I think this is interesting as well, where we're seeing that there is a path for an embedding here, and this embedding is actually coming from this text embedding here. And like, this is essentially how you go in and like, introduce embeddings into your vector search, and then search using the embedding models that you've actually selected. So let's see if that search is up and running at all. Let's go back into the app here. I hope it didn't refresh. So how do we get the embedding models? Yeah, so you would go in and actually search for your own embedding models, and you could find a bunch of different ones on the link that I just popped up on the screen there. Oh no. Um, Vegan options. Let's do that in Westside. Hopefully that just goes faster. Okay, see. So I think my query before was just a little bit too long. I don't think the map is going to work. It said something about loading in an hour. So hopefully, like, later on when you're playing around with this at home, you'll be able to kind of take a look at the map yourself and see all of the different locations for vegan options. But here, obviously, it's giving us some pretty good examples. These are Crossroads Kitchen and then Platt Food and Wine. And then as an alternative, you can also go to the Loving Hut. It offers affordable casual dining, which is pretty interesting because a friend of mine actually owns that restaurant, so I'll be sure to tell them later that it came up during one of my during one of my workshops. But yeah, I mean, that's it for the example here. I don't know if you have any questions, but let me just go ahead and jump back into the workshop here. So let's go ahead and recap what we learned. So the first thing is that embeddings are an array of numbers that capture semantic qualities of data. The second is going to be embeddings are generated by specific machine learning models. And then the third thing is that embeddings can be added in place into existing MongoDB documents. So this is kind of going to answer this question for you, Skay or Skylar, not sure. Basically, you're getting the embedding models from a third part. You're getting it from a third party, something like basically it's something that's already been pre-made for you, and then you're going to go in and actually embed those embeddings into your existing MongoDB documents. All right. So let's dig a little bit more into vector search. So basically, now that we know what embeddings are and how to generate them, we can see how they actually fit into vector search. Remember that the embeddings themselves are meant to map data that's similar in meaning and close to each other in the vector space, which is, something I was like basically trying to explain earlier. So given a user query, in order to retrieve results using vector search, you'd first generate an embedding for the query, then use the same embedding model that you use to embed the rest of your data and retrieve items closest to the user query embedding in vector space. So once again, this is what I explained earlier. Your query goes through the embedding model, gets the basically the vector assigned to it, and then here it goes in, and then you get all of the information that is close to it semantically and in vector space distance. So without going too deep into it, we're going to briefly talk about how vector search works in MongoDB. So in MongoDB, there is an algorithm, and it's called the Hierarchical Navigable Small Worlds, or HNSW for short. And the way it works is it's basically by creating a layered connected graph. And the embedding vectors are going to be nodes. And each node is then connected to a specific number of nodes or nearest neighbors based on their distance in vector space. So here, this is how you could actually visualize it. At each layer, you have an entry point, and then you're going to move from one node to another in that layer until you can't get any closer to the vector query in that layer. Then you're going to move to the next layer, and you're going to repeat the process, and you're going to keep doing this until you basically reach that final layer. And then you're also notice, like, the actual connections start off pretty sparse at the top, and then they become denser as you go further down. So at the higher layers, think of it as like a water filter. It's really doing a very coarse filtering at the top, and then as you kind of go down further, the material to filter gets finer and finer, and once it reaches the bottommost layer, it fans out, and it's just going to find the closest neighbors there and give you the most accurate results possible based on how you're actually searching. So if you want to learn more about hierarchical navigable small worlds, this is a deep dive that you can take a look into. It's pretty interesting, actually. I was looking at this the other day. It's very interesting how the search actually conducts itself and progresses through all of those filtration stages as we just visualized. So if you're really interested in it, I think it's really worth the deep dive there. So the goal, as I mentioned before, the goal of the vector search is to retrieve the documents that are in the closest proximity to the query vector within a vector space. So, the problem with this is in 100 or 1,000 dimensional space, what does the proximity or distance even mean? So distance in vector space is essentially calculated using mathematical functions. And here you're going to have 3 options in MongoDB. And the first one is going to be Euclidean distance. And this is going to measure the absolute or straight line distance between the 2 vectors. As you can see here, you have dog and cat. And this just measures the Euclidean distance between the 2 of them. Then we have the dot product that multiplies 2 or more vectors to measure alignment between them. And the thing to note here is the large numbers in the vector have a big impact since you're multiplying the values. So here, your dot product vector space distance is going to be 14, but obviously the 4 and the 3 are heavily skewing the results here. So that's just something to take into consideration if that's how you're going to measure distance between, one piece of data and another. And then finally, you have the cosine similarity, which looks at the angle between the vectors. So previously, we saw that the dog and the cat was just measuring the distance, and and then also with the dot product, the difference between the vectors is pretty high. So here, if you're just using the cosine similarity, it actually shows that there's a greater similarity between dog and cat using this measurement versus the other 2. So this is where it's actually helpful because it just measures the angle between the vectors, which is always going to it's basically going to still get you more results, but also probably improve the accuracy of the results that you're also getting. And this is just, as an aside, this is one of the more popular distance metrics for vector search out there. So once again, if you're doing a deep dive into any of this stuff, make sure you check that out as well. Cosine similarity. So let's recap real quick. First, vector search retrieves documents closest to the query embedding in that vector space. Next, you're going to use the same embedding model to embed your query as well as the data that you're searching on. And then third, the distance in vector space is calculated using mathematical functions. So you have the cosine, you have the dot product, and then you have the Euclidean distance. And then lastly, the cosine similarity works well with most embedding models. So now that you understand vector search, how it works in MongoDB, let's look at how to perform vector search queries on your data in MongoDB. So there are going to be a couple of steps here. First, you're going to generate the embeddings, which is something we've already gone over. And by generating the embeddings, I mean going and picking an embedding that you want and then rolling with that. The second one is going to be to create a vector search index. And then finally, you're going to send a vector search query. So the way this looks is if you're creating the vector search, once you're created the vector search index, you're going to need to do that in order to efficiently query your vector data. So the index specifies the path to the embedding field in your documents, the number of dimensions in your embedding vector. And this is going to depend on the embedding model you use, obviously, to generate the embeddings, and the similarity metric that you're specifying to measure the distance in the vector space. But obviously, you have a few options here. In this case, it's going to be the number of dimensions you're using is 512, and then the similarity metric that you're using is going to be the cosine distance. Oh, cosine similarity. Finally, this is how you would perform a vector search query in MongoDB. So vector search is actually part of MongoDB's aggregation framework. And aggregation pipelines are just a series of data processing steps. I'm not sure, we didn't cover them in the previous session, but we've covered them in sessions from past Global Hack Weeks. So if you want to take a look at what aggregation pipelines are, you can check out the workshop that I did for MongoDB 101 during Global Hack Week Beginners Week. But essentially, it's just like a list of different things or commands and filters and things that you would use in order to sort of like drill down to a specific data set. And yeah, essentially a list of instructions that you're giving to your database. So here, as the example, here's the example. You're creating a pipeline, and this is a vector search. Obviously, you have the embedding, and then this is the query vector. So this is the vector this is the embedding that's being assigned, or the vector that's being assigned, pardon, to the actual query that you're putting into the database. Here, the num candidates that you have are 150, and you're limiting your search to 10. And then here, this is the basically the thing that you're looking for. This is the filter that you're looking for, the project that you're looking, the $ project that you're looking for. Just as a quick aside, the num candidates is a parameter in the MongoDB Atlas $ vector search stage that specifies the number of similar documents the vector search algorithm will check before returning the final results. So here it's only going to check 150. And then also for here, the project, the $ project stage that follows only returns the title field from the return documents along with the similarity score returned from the vector search. So once again, it's only going to return the things that you ask for, and then it's going to give you a similarity score. All right. Yeah, I mean, we could take a look at the example again if you'd like, and I can kind of show you once again what that looks like. So here we kind of jumped into it because the application was a little slow earlier, but just to go back into what that looks like in real life, or what the aggregate pipeline looks like for that. So this is like basically the vector search. As you can see, it's an aggregate pipeline. It's doing the same thing, and the $geo near is just like something that is specifying to get things that are close to the geography or the location that's being provided. And then here you have the add field. So you're going to add a search trip and ID, and then a trip ID generation time. You're going to get it timestamped. And then finally, you're going to merge this into the smart trips. So smart trips, I believe, is like the feature where you're actually creating the vector search that will then go in and generate the like you'll feed it into the generative AI to give you the responses that you want for the restaurants that you want to retrieve. And that's essentially it. Any questions there? Looks like we're pretty quiet on the home front here. We are about 40 minutes in, so what I'm going to do is I'm just going to jump right into the next section here. All right. So I don't know, based on the stuff that we've already learned, it's starting to seem pretty easy to go in and do vector searches on your own. You can see how your vectors can coexist with the rest of your data in MongoDB. So effectively, MongoDB Atlas Vector Search, it just provides you with an integrated platform for your operational as well as your vector data, and it's both queryable via a unified MongoDB query API. So you could use the API for this stuff, and also you could do it programmatically, as we just saw. Since your operational and vector data reside in the same collection, your data is automatically synchronized with vector indexes that you create on the collection. So, once you start inputting the embeddings, all of your data will be automatically embedded for you as well, as long as it all lives within the same collection. It's a fully managed service, and you don't need to do anything or worry about maintaining the infrastructure. So this is really hands off, and it's something that's going to be it's just going to be really convenient for you as a developer if you're utilizing the service. So definitely check it out, MongoDB Atlas Vector Search. I added the MongoDB Atlas sign up to the last workshop, but you can check it out here. And we've got a question here. Are the aggregate pipelines readily available on MongoDB? No, but you can go in and generate them yourself pretty easily. So the way I would look at MongoDB's aggregate pipelines is, if you're familiar with, filters or like select alls in SQL, this is essentially a very similar process where you're just kind of like, instead of having an entire query set up, you have a pipeline that filters through data and like in a step-by-step basis. So the first step could be like, grab me everything that grab me all of the people in the database whose last name starts with A. And then the next step could be, out of these people whose last name starts with A, could you filter down to the people whose first names start with B? Now it's only got the people whose initials are B and A. Now it's like you could filter down for age, and then so on and so forth. And then at the end of it, basically what your results are going to be the results of having gone through all of those specific steps one by one. And it's something that you can take a look at in terms of actual functionality. If you'd like, you can go into the MongoDB documentation, and I'll put another link into the chat here for you, 925 MongoDB docs. And you could literally ask the AI assistant, how do I create an aggregate pipeline? And it'll give you the documentation for that specifically. So it's not, like, to answer your question, it's not something that's already there. It's something that you would need to set up specific to your database and the query that you have. All right, let's recap. All right, so to perform vector search in MongoDB, you need to generate embeddings. Oh, I think this is oh no, it's not. Okay, you need to generate embeddings, create a vector search index, and then send the query. The number of dimensions in the vector search index depends on the embedding model that you use. And then the vector search should always be the first stage in a vector search aggregation pipeline. All right, so optimizing your vector search queries. Now that you know how to perform a vector search on a small data set, let's jump into optimizing those vector search queries. For large data sets, let's talk about some techniques to optimize your vector search queries here. And the first thing you could do is you could start with pre-filtering. So in many cases, we see folks wanting to filter the vector search results based on certain business logic and recency. In your case, like, this might not be as relevant to you if you're building for hackathon projects or even at Global Hack Week, but let's say you're taking this into your professional life. You're going to want to go in and start to utilize this information on the larger data sets that you're working on. So in MongoDB, you can actually apply conditions as pre-filters for your vector search. So essentially, first, apply the filters to your collection to produce a filtered set of documents. And if the number of filtered documents is less than the number of vectors or results to be returned, an exact nearest neighbor search is performed, and this can be slow. But if the number of filtered documents is more than the number of documents to be returned, an approximate nearest neighbor search is performed. And when the hierarchical navigable searchable worlds graph is reversed, it only considers document IDs that are present in the filtered set. So if we take a look at this document here, where we have this, large amount of documents, we're pre-filtering it. We have the filter IDs in a number of documents already. So as long as the number of documents is less or equal to the number of basically dimensions that you're searching for, then it's going to skip certain things. But if it's not, then it's going to do it anyway. So here it's skipping the, where is it here? It's skipping the approximate nearest neighbor search, which is like basically it takes a really long time, and this basically cuts out a lot of the time that you would take having to do that type of search. Whereas here, it just it does the HNSW graph, and it traverses through it the filtration process that we kind of talked about earlier. So yeah, definitely pre-filter. It's something that will save you a lot of time, and it'll just make your searches a lot more efficient. Okay, as you can, sorry. Those were animations. So in most cases, as long as your filters are not too restrictive, or in other words, as long as the approximate nearest neighbor search is performed, pre-filtering actually helps with the vector search latency or the efficiency or just the speed, while also improving the accuracy of your search. So as you can see here, pre-filtering versus post-filtering, you might be asking why pre-filter and not post-filter vector search results. And to answer that, let's look at this example where we have a vector query, a query vector, and its vector similarity to documents in the books database we've been referencing. So now let's say someone has indicated that the only they only want books that have less than 100 pages, right? If we apply this as a pre-filter and K is set to 2 to only retrieve the top 2 candidates from the vector search, then the vector search will exit as soon as it finds these 2 candidates. Whereas if we apply this as a post filter, so this is a pre-filtering, it's going to exit as soon as it finds those 2 candidates. Whereas if we apply this as a post filter, there is, sorry, we're only going to end up doing the full search and grab these 2 documents with similarity scores of 0.95 and 0.92, only for the filtering to drop the results. So basically, it's like if you post filter, you're still going through the entire post filtered thing. Whereas if you pre filter, you're only going your search is going to stop as soon as you get the, sorry about that, as soon as you get the actual results that you're looking for. So in other words, basically, pre-filtering is way superior to post-filtering in this case. So if you want to add pre-filters to your vector search, it really involves just 2 things. The first is you're going to update the vector search index definition to include the filter fields. So here, type filter path pages, and basically what that means is going to filter on those 2 things. So on the number of pages. So the other change is in the vector search stage of the aggregation pipeline. So you'd simply go in and you're going to include the filter containing the pre-filter expression. And in this example, we have the filter set to pages of 200 or less, as you can see here. So that's, essentially the way that you're going to pre-filter. And to recap really quickly, you're going to use pre-filters to filter vector search results based on certain criteria. Then you're going to pre-filtering can slow down the vector search if the filters are too restrictive. So make sure that, the amount of results that you get are actually larger than the amount of results that you're meant to filter through. And then post-filtering is not recommended. All right. So you could check out this QR code. You can go to this link. It's going to be, an AI learning hub that you can go in and kind of deep dive into a lot of the different things that we've already covered today. And I'll go ahead and drop that link in chat here for y'all. And, that's really going to be it. We've learned so much today. We've learned about like vector searches. We've learned about vector distance, embeddings, in the vector search context, of course. And then we've also learned how to pre-filter and filter results and set up aggregation pipelines with vector search itself. So with that, we are going to jump into Q&A. If y'all have any questions, let me know. If you want me to just go back and review anything, that's also something I can do. Entirely up to you. All right. So while we're waiting for folks to come in with any questions that they may have. All right. Do we apply filters for post filtering as well? So, as I mentioned before, you're not going to want to do post filtering. So the reason for that is post filtering versus pre filtering. So here in this example, let's say you want to find something, all of the books that have less than 100 pages. If you pre filter, what it's going to do is it's going to exit as soon as it finds these two things. As soon as it finds, especially if you're just limiting the number of items that you want to retrieve to the top 2 candidates, it basically your query will stop as soon as it finds these 2 items. But if you post filter, what's going to happen is it's not going to have any impact on the search latency because it's still going to go through all of these items before actually returning the top 2 results. So that's like the main reason why you're not going to want to post filter versus pre-filter, because essentially it's not really adding a lot of benefit to the efficiency or the latency of your search. Cool. There are a couple of things. I don't know if y'all folks if everyone here was around last time, but we do have a couple of challenges that we are currently doing for Global Hack Week Data Week. If you want to go in and kind of use some of the stuff that you learned about vector searches here, you're going to want to check out these challenges here. So the first one is going to be claim your RAG with claim your RAG with MongoDB skills badge. Next one is claim your vector search skills fundamental skills badge. And then if you were in the previous session, you're going to also claim your relational to document model skills badge, as well as the sign up for MongoDB Atlas account and any of these things. You could actually do that now if you'd like. And yeah, it looks like we have another question here. So let me just jump into this really quickly. Can we use sparse vectors? Can we use both? I'm not sure what that means, to be honest. I'm not very familiar with that. We could kind of like look into it together if you'd like, but let me just jump to this next question first. Since post filtering is slow, but its usage is relevant to many scenarios. Since post, okay. There may be ways for you to utilize post filtering. Obviously, if it's useful to you from a different perspective, I'm not saying don't use it. I'm just kind of pointing out some of the drawbacks that you may have if you're only using post filtering. If you're using pre filtering and post filtering, there may be benefits to that. But I would say if you're looking to filter your data in any way, shape, or form, you should first start to pre filter so that you can actually improve the latency of the search, and then you can post filter in order to further optimize your search for speed or for latency or for accuracy, whatever the use case or the end goal for you might be. As far as sparse vectors are concerned, I actually don't know what sparse vectors are, and I'm not ashamed to admit that. Let's see here. Let's jump in and do a quick search. What are sparse? Actually, you know what? Instead of this, let's go to sorry. MLH.link, GHW data 925, MongoDB docs. And I'm cognizant of the time here. We have a couple of more questions here. I did want to display this earlier, so we're going to ask MongoDB AI. What we're going to do is we're going to take this question. Can we use sparse vectors? Can we use both? For hybrid search. I got you. Can we use sparse? Can we use sparse encodings and dense encodings for hybrid search in MongoDB? And I'm just gonna let's see what it says. MongoDB Atlas Vector Search primarily uses dense vector search representations for semantic search. And here's how sparse and dense encodings fit into the hybrid search experience. Sparse vectors are typically used for traditional full text search like Atlas search. These vectors are mostly zeros, representing the presence or absence of features such as specific words, whereas dense vectors generated by neural network models called embedding models represent data in high dimensional space with mostly non-zero values. So dense vectors capture more complex and nuanced relationships in data and are used for semantic and vector search. For hybrid search in MongoDB, you can combine full text, sparse vectors, and vector, dense vectors, vector search or dense vectors in same query pipeline, while Atlas Vector Search itself uses dense embeddings for semantically similar. Atlas Search can provide text relevance using sparse encodings. In summary, you can leverage both in a hybrid search workflow in MongoDB. The actual hybrid search capability comes from combining Atlas Search with Atlas Vector Search in your application logic or aggregation pipeline. And then it has some examples. That's pretty cool. All right. Well, if you haven't used MongoDB's documentation so far, definitely check it out because it seems like it just pretty much hit this answer out of the park. Did that answer your question? Love to see it. Love to see it. Alrighty. It looks like we are basically running close to time here, and we've also essentially covered all of the material that we were meant to cover. So with that, I just want to thank y'all. Definitely check us out at the website ghw.mlh.io. Check out the challenges, check out the workshops that are coming up and the sessions that are coming up a little bit later today. Another thing, if you have any questions that you can't get answered on your own through the docs, or you just want to basically bounce some ideas off of anyone else, there is an Ask MongoDB channel on our Discord server. So go to discord.mlh.io and you can get set up there. Ask any of the questions. I know some folks were also asking about the content that we shared. So I'll create a PDF of the slides and I'll share them with y'all there. You'll be able to go in and kind of review the content from that end if the recordings are not enough. But outside of that, this has been really cool. I love that y'all stuck around. Thank you so much. I appreciate you calling me interesting and the content interesting. I don't know if I was interesting personally, but definitely MongoDB is interesting. And we've got people who learned a ton, Way in particular on YouTube. And folks that appreciate the content, really appreciate y'all. Once again, I hope y'all have a really good rest of your global hack week, especially for day one. We've got a ton of different content that's coming up. I think Way is coming up right after this. He's going to be doing some really cool things, probably better than me, but I'll let y'all be the judge of that. Outside of that, it's been cool. I appreciate y'all. I will check y'all out later. I'll see you again on stream this Monday. So until then, have a good one, y'all.